We can start the recording and we can start our webinar. So thank you all for being here and welcome to this new SEM webinar that is devoted to the topic of process and product sustainability in additive manufacturing. Let me say that SEM is a European-funded project with the target of developing a sector skill strategy in additive manufacturing. And in today's webinar, we will explore all the sustainability aspects related to additive manufacturing processes. And we will go through how additive manufacturing can contribute to the twin transition. We will present some novel eco-design solutions that can be adopted in this framework. And we will also go through some real industrial examples in the field of fused filament fabrication. So my name is Marco Grasso. I'm an assistant professor in the Department of Mechanical Engineering of Politecnico di Milano, and I will moderate this webinar. I also thank Gabriele Favaro from Sesimo, who will help me with the technical stuff and will help me with the moderation of this webinar. I think we can start. So let me introduce first our speakers. We have Professor Bianca Maria Colosimo from Politecnico di Milano. Bianca.
Hello.
Hi, Bianca. We have David Santos Gonzalez from the Idonial Technology Center. Hi, David.
Hello. Hi. Good morning.
And we have also Dr. Ioannis Kokinopoulos from IRES. Hi, Ioannis. Hi, John. So I would just ask you to keep the microphone switched off. If you have any questions, you can write questions in the chat. We will have a question and answer session at the end of the webinar. Just in case of the first presentation, that will be the one from Professor Colosimo, since she will need to leave at some point in time, maybe if you have questions on that specific presentation, we can anticipate them just at the end of the presentation. Let me also say that in the chat, you will find a link for a survey. We will ask you to please fill this survey to provide us with your feedbacks about this webinar at the end of the webinar. So please take your time at the end of the webinar to go through that. So let's go on. So the first talk is from Professor Colosimo, who is full professor and deputy head of the Department of Mechanical Engineering in Politecnico di Milano. She's one of the founders of the ADMI Lab, a research lab covering all the major research and industrial innovation aspects in AM. And the title of her presentation is Sustainability of Additive Manufacturing Processes and Products Towards the Twin Transition. Bianca, please, the floor is yours.
Okay, thank you so much. I think you can see my screen now.
Yes.
Okay. So good morning, everybody. What I'm trying to, let's say, provide you with is some sort of general overview of the dimensions that I feel are really interesting from the viewpoint of additive manufacturing technology. So we will have a look to many different technologies, especially on the side of what is called the twin transition, which basically means, let me see if I can, okay, on the one side going digital and on the other side going green, let's say, even if I should say that sustainability is also in a broad sense putting the man inside, let's say, the loop. So I will mainly focusing on the environmental aspect and features, but I should say that we can even extend this type of connection of AM with the sustainability concept in a broader sense, let's say. Digital why? This is just to provide you with the single steps that we are all dealing with when we are using additive manufacturing. So from the one side, we are really on the digital world for a long time of the process chain. So we start designing a new product and we use a lot of software for doing this job instead of, let's say, going with a trial and error in our lab. Then we can decide and plan the right material. And on the other side, we can start having some sort of digital twin so we can enjoy simulation for having some guess on what is going to happen while we are producing part. Then we're moving, and this is for sure the physical side, we are moving to the machine. Despite of the specific process, it can be powder bed fusion. I will be mainly focused on additive manufacturing as a production process. So I will spend a few words on metal AM, but also on composite AM. So dealing with, let's say, products that have some, at the end, functional, let's say, performance that are needed, more than just prototyping, let's say. But again, even if you are on the machine, so you are in the physical world, you can enjoy a lot of information that is coming out from the process, since there's, let's say, AM is an open process from many different viewpoints. So you can gain a lot of information in situ and in line to have some sort of idea of what is going on. And then you can move. And again, the final check and the offline, or let's say ex situ qualification of the product can be done with some non-destructive testing like X-ray CT, and so you can have a digital, let's say, image of what has been the final part produced and all the defects, and so you can go back to the design maybe. All these digital side, and this is why AM is usually referred to as an enabling technology in Industry 4.0, because it's really, really digital from many viewpoints, is enabling basically many different directions in which I can feel, and maybe we can highlight how AM is also green, let's say, moving in the direction of being a green technology. The first big feature and the first big, let's say, direction in which you can move green is referred to design for, let's say, life cycle in a broad sense, or for green transition. So since AM, by definition, allows you to have complexity for free, let's say, or almost for free, you can enjoy these additional features for designing new products that, first of all, are lighter. And so weight reduction, it's one of the key ingredients for reducing fuel consumption. And this is why all aerospace companies are moving to additive. No way of escaping from that, because they need to have weight reduction that are quite impressive. And I should say that weight reduction means also waste reduction, because you are using material and you are putting material just where it is needed. So it means that you are also reducing the material that we are using. And there's also a side effect related to the cost reduction. You can enjoy the functional, let's say, capability of the newly designed concept, like, for instance, lattice structure, even for improving efficiency. That is has some side effect also on the way in which you are consuming resources, because in case you can produce something that is lighter, but also the lattice structure have the capability of having some better performance in terms of fatigue and wear resistance, heat dissipation, which means, again, some energy related, let's say, saving, and high energy absorption capacity. So they are used in many different sectors, from the aerospace, but also automotive and also biomedical, let's say, direction, for improving and taking advantage of all these capabilities. Again, thinking about the design, the freedom of design, or the design freedom, is not just a matter of making something that is lighter, but there's another, I think, very, very important feature that you can enjoy, that is reducing the number of components. Reducing the number of components, usually, and this is the clear example of DG fuel nozzle, but you have a lot of examples in which you can really move from a system of many different components to just one big part produced by AM. This means, for sure, having some lifetime extension, because usually where you are, let's say, bringing two parts together, it's where the part can, or the system can be a little bit less efficient in keeping the lifetime, and so less reliable in terms of function at the end. And there's also some side effect that we will see in a while also on the number of components that are traveling worldwide for the logistic impact. And this is also going to have an impact on the environment, because if you have a lot of components that are arriving from one side to another, it means moving mass. And so again, this is some sort of consumption of energy. There's an additional very important dimension that we can explore, that is in machine tools production, because additive manufacturing allows you to have some sort of conformal cooling, and so it means better use of the energy, reduction also in case we are talking about molding of cycle time, so the time that you need for producing the final parts when you are using these molds that has these conformal channels inside. And you are also able to increase the final quality, which again means reducing scraps. We will spend some time in what does it mean reducing scrap, and so going in the direction of a zero waste production, and why this is another dimension for thinking about sustainability. Material. There's a lot of attention. This is just few, let's say, mention and highlighting that you can, for sure, and there's a lot of research going on in using waste for producing new filament, new polymers, and on the other side, there's a lot of interest now coming out in also using some existing and recycled metal material for producing powders for AM. So it means that you can maybe combine fresh powder with recycled powder, or powder coming out from recycled material for having a second life for let's say chips, for instance, or other type of powders. And there's a lot of interesting studies going on in this direction. And clearly there's a lot of attention in how many times you can reuse and recycle powder. So what are the best practice in terms of reusing the powders and so avoiding waste at all? But in the case of metals, and also in the case, which are, I think, more interesting in terms of the impact on the environment of polymer or composites. There's a lot of, let's say, also research going on in this direction of thinking about second life of what you have been printing. Eventually, one last, I think, very important dimension is going to be, as I was saying, related to the amount of parts that is traveling worldwide in conventional manufacturing. So the big effect that, and the big impact that additive manufacturing is supposed to have on the supply chain. So it means that with respect to traditional manufacturing, which you have all the material resources provided to some specific hubs when I'm producing components, and then components are traveling worldwide. And we saw in these days how connected we are in traveling of components for the final assembly and then for retailing. All these steps of things that are moving worldwide can be, at least in principle, this is the long-term vision, changed completely, because AM can really, since it doesn't need tooling, dedicated tooling or fixturing, at least in principle, I can just send a digital file now in any part in the world and where there's a printer, and they can start printing at that point in time. So it means that I'm just moving information rather than material, and I can print where and when I need it. So the when is also very important, because it means that I can use, and this is a well-known field of interest for AM, I can use additive manufacturing for spare parts production. So I don't need to have really huge, let's say, working process or parts that are stored, because I will use maybe in the future if something will get broken. And on the other side, there's also some specific technologies like the DED, the direct energy depositioning, which I can use AM for repairing something, so extending lifetime. So I think I've been providing an overall picture of many dimensions that we can explore for making AM and enabling technologies for green production. And I like, let's say, this cycle that is basically describing all these ingredients I was mentioning, from the new material option to the design freedom, and so the capability of using just material where it is needed. And then sustainable manufacturing, that means I can have this centralized production and inventory control, so avoiding, let's say, waste of components or materials. And on the other side, and this is something I'm going to just touch in this last part of my presentation, I can even think about producing better products and simplify the resource use, also thanks to the digital side of AM, in one specific direction, that is going to move to some sort of zero waste production. So I want to point out that the big advantage of the digital side of AM, so the fact that I can even put a lot of sensors inside the machine, and so being able to have at each time instance some sort of digital ID of what I'm producing, is a relevant direction, I think, for future research that is combining the digital as an enabling technology for moving green. This is on the top side of this slide. You can see the, let's say, patenting attention coming out in the AM world. And you can see some bars. The first one is referring to the first 10 years of existence of AM technologies. Then the second 10 years from 1998 to 2007. And then the last bar is showing let's say the most recent decade. And the different colors are showing patenting that are depending, I can just show a few examples, on the machine. So I'm inventing a new process or I'm changing something on the machine, and this is why the new patent has been issued. Or on the other side, if you move to the black side of the bar, you can see that this is just related to invention, related to data acquisition and data processing. And so you can see that a lot of attention is not just on the physical side of AM, but also on the way in which I'm using the digital information I can gain in AM. As a matter of fact, 30%, 1/3 of patents is focusing on this type of, let's say, direction. And I like also the, let's say, the idea that is coming out from this report that is saying that consistency is the Achilles heel of 3D printing, because, I mean, in order to have additive manufacturing to grow in terms of the capability of solving real industrial problems, we need to face, unfortunately, the low stability or let's say the complex and the high scrap rates that we have still in AM, especially in the context and in the sectors in which additive manufacturing is used. Usually we're using expensive materials, so creating scraps or let's say means wasting a lot of expensive materials, so money and also precious material, and we know that we are facing a shortage of materials. Usually AM has the other problem of asking for long processing time, so it means that if I'm producing something that at the end will result defective, I've been spending a lot of energy and long times just producing something that I need to scrap. And the other dimension why I do believe that moving zero waste, I mean, it's relevant in AM, it's that usually you're using AM in biomedical sectors, aerospace sectors, where the zero defect is mandatory. I mean, there's not that you can really do something for creating something that is defective, or you are not tolerant to defective part. And then there's the additional issue that this design freedom usually allows you to create small batch or customized production. So it means that each time you are changing the part that you are producing, so you don't have time for learn how to process to optimize the process, how to set process parameters. So you are really asked to, let's say, be able to make first time right, let's say this way, because you have few parts for learning how to optimize the process. In all this picture, and looking to all the defects that you can face when you are producing parts, so from in case you are creating complex shapes, there are sometimes, especially for overhanging parts, geometrical and dimensional errors. You can have thermal stress, and so you can have some bending. You can have incomplete job because something is happening in terms of the spreading or the let's say the energy that is selectively melting, in this case the powder. And unfortunately, there's a big enemy that is on the bottom hand side of this slide that is coming from pores and porosity, so what are called volumetric errors. And if you look to porosity, there's another big issue is that this short scheme of the window of processability, if we are thinking to laser powder bed fusion, so on the y-axis the laser power and on the x-axis the scan speed, the window called in this plot 1, it's the only window in which I have parts that, let's say, have the minimum amount of pores inside. Unfortunately, if you are moving to other windows, in this case, it is named 2 or 3, the amount of energy that you are delivering is too low or too high, and this is causing lack of fusion or overmelting porosity that are big guys. I mean, to be avoided in terms of the final functional performance of the part. This is just to say that the process optimization maybe needs a lot of steps and a lot of trial and errors issues. So it means a lot of waste, because it means, again, In order to be able to go in production, you need to make a lot of attempts trying to find the best window, which depends also on the geometry you are producing. So it's not just a window related to the specific material you are producing. And so my vision in this direction is really taking advantage of the digital world, in this case, taking data at the digital side of the part of the AM, which is combined with the big data mining capability that we have now, so that you can take a lot of information. Instead of just playing with process and look into the final product, you can gain a lot of information in situ and in line, which, and I will show some example, to have some sort of real-time ID of what you're doing, just to stop if something is going wrong, or maybe try to correct and make something in order to heal, let's say, your error and heal the part while you are producing some defect. I should say that this direction of moving green also, thanks to zero waste or zero defect, is growing. The attention in this specific field that is also named in situ monitoring is growing at a high speed. Also because you have a lot of different directions you can act on. So you can have some sort of information coming out from the signals. I will show a few examples just to provide you with some sort of look of what are the many directions you can play with. You can have information coming out from just the image of the powder bed and the printed slice. You can even go in deeper detail and see what is happening in terms of scan track if you're focusing on powder bed fusion. And going in deeper detail, you can see the melt pool just to see how stable the melt pool is in terms of size, shape, intensity, and temperature distribution. And there's a lot of attention now that is rising also in looking beneath the layer you are playing, trying to see if there's something going on in terms of crack or subsurface pore. I should say that this level number 4, it's the most difficult one to be faced, let's say, with in situ monitoring. Just some examples. We have been doing a lot of research in this direction in the last years. This is just an example, just playing with signals. I can just take all the signals that the machine is taking advantage of, and I can even build some sort of region, thanks to big data mining or machine learning, where everything is supposed to be safe. If I'm, let's say, these signals are providing then a fingerprint that is inside the green side, I'm safe. On the other side, the red crosses are showing a case in which I will have a defect at the end. And you can see that these red crosses are moving out of, let's say, the in control region. And so I can even, at a given point in time, stop the machine and maybe create some sort of corrective action. In this case, there was a wrong, let's say, the position of the powder. We can even take the picture of the part of the slice part as soon as I've been printing the part layer-wise. So while I'm in the machine and I'm printing the part, this is a direction we do believe it's really, really relevant, because it's some sort of geometrical inspection that is done in real time, layer by layer. At each layer, you can reconstruct what you have been printing. You can compare what you have been printing with the nominal shape you should have been printed at that specific layer. This is the red border is shown, while the white is the one that you have been printed at one specific layer. And on this real case study, we saw that the defect that at the end was resulting was almost easily, let's say, detectable in situ and in line just by playing with this image of what you were printing. And we can clearly move ahead and think about this concept even for very complex shape like lattice structure. We have been, let's say, showing that you can in situ reconstruct the geometry of a lattice structure that is quite complex to be reconstructed, having some sort of in situ reconstruction that is quite, let's say, consistent with respect to what you can see ex situ, thanks to the X-ray CT, again, layer-wise. And you can even think about a new dimension in which this voxel-like, let's say, picture, it's not more about pixel, you are moving in a 3D shape. You can even use a similar concept to detect if something is wrong, let's say, in complex shape. So basic lattice on manifold or something like that. You can develop some specific tools for doing this job as well. A few other words on other, let's say, quite interesting direction in which you can start even not just playing with image, but playing with videos. And in this case, you can see for instance, problems related with hot spots or cold spots. So in video, thanks to some sort of in situ and inline imaging and video imaging of the frames you are producing, you can detect in situ and inline a hot spot that at the end it's going to result in a defect, or even look to the, let's say, melting the products that are coming out from the melt pool. In this study, we have been playing with sputtering. So if you can see the signature of the sputters coming out from the melt pool, we saw that this sputtering phenomena can be linked to some sort of over melting or under melting that at the end results on porosity, lack of fusion or over melting porosity. Just looking to the sputter signature. So just looking to some sort of idea of what is coming out from the melt pool. I think I'm moving to, let's say, close to last examples, just to show that you can even not just play with video, but also with thermal video. And in this case, you can have some sort of history of what is happening in terms of the thermal cooling, which is observed at each specific location, thanks to this thermal imaging that in this case is done on metal powder bed fusion. At each location, you can follow the cooling history and maybe derive or see that in some location, the cooling history is too fast or too low. And so this is going to create problems in terms of what you want to do at the end. And we have been doing exactly the same job also. Unfortunately, this is a video that I cannot show. Sorry, I was moving. And we did a similar job also in composite and extrusion-based composite in a work we did together with MIT, and showing that again, thanks to the thermal imaging, especially if you're moving large, and large means long processing time, a lot of wasting materials if the part is defective, so everything is amplified. And keeping zero defect on large structure, this is the wide area additive manufacturing, it's going to be a mess. And so by, again, in situ and in line, looking to some sort of defects, this was a cold spot. This is going to let you see that there's one specific problem in real time, let's say. My one last comment is just on not just detecting the problem, so detecting the defect, but also trying to correct the defect. That I think it's going to be the next dimension of the attention. We need to pay to, I mean, in terms of community from the industrial and the academic viewpoint. And this was a study that I think is worth mentioning because it's thinking about the concept of feedback control. So I'm looking to the ID of what I see. In this case, we were looking to the melt pool in real time, and we can recognize that there's the melt pool intensity is going to be too high in one specific location of the part we are printing. But what is new is that in this case, we didn't say just, okay, let's stop, because we saw that this red location means that the melt pool is delivering too much, the system is delivering too much energy in that specific location, and so the melt pool is revealing that something is wrong. What we did is, okay, but can we correct in the next layer the problem that was, as you know, you are remelting part of the layer you have been printing, or sometimes all the layer that you have been printing. So by, let's say, creating a feedback control action in the next layer, so a layer-wise control, this is going to let you arrive to stability quite soon. And maybe this is also a way for thinking about process optimization done in situ and in line. So you can play with process parameters just by looking to the signature of what you're doing and find the best setting of parameters thanks to this image. And in this case, it was some sort of, let's say, ID of the melt pool. So a lot of directions, I think, are going to, let's say, concern the future in trying to not just detect the problem, but also, let's say, correct the problem. So this is the end of my overall picture that is kind of combining, as I was saying, the green on the one side transition and the digital transition. So the AM, it's an enabling technology in the digital manufacturing for sure, but you can really take advantage of using this complexity for green, let's say this way, and this digital ID for green instead of, let's say, using for just reducing costs or moving large or having other type of, let's say, challenge we all have in AM. Okay, this is my last slide. Let me see if I can keep back control.
Thank you, Bianca. Thank you, Bianca, for this presentation. I think you clearly showed that more intelligent machines can lead to better quality processes, but also more sustainable processes. And so digital and green goes actually together, and they are actually twins. So thank you for your presentation. I saw that there was a reaction in the chat from Luca Biagini mentioning some application in sustainable hydraulic system. I don't know if there is one question or comment from Luca. If you want to switch on the microphone.
I was just hello. I was just pointing out that neither we're already using additive manufacturing, and with for our hydraulics application. And yes, we're pointing very hardly on that.
Thank you, Luca. Is there any question or comment for Bianca?
Okay, I think maybe we can move to the next presentation.
Yes.
I'm fully available in case you are also, let's say, interested in some one-to-one chat after the webinar, obviously.
Yes, you have the contacts of Bianca, and if you want to go through the recording, you will find there the contacts. And okay, thanks again, Bianca. I think we can move to David. So Dr. David Santos Gonzalez, he is from Edonian Technology Center, where he is a project manager in the advanced manufacturing area. He is working on innovative technologies in the fields of design, engineering, and manufacturing, as well as standardized systems related to quality and R&D. The title of this presentation is Eco-Design as a Structured Approach to Implement Sustainability in a Product Life Cycle. So David, I leave you the floor.
Okay, hi to all of you. First is first. You are seeing my screen, right?
Yes.
Okay. So, well, I think that Marco has made a very good presentation of me. I work at Additive Technology Center in the Advanced Manufacturing Department, which has been for several years linked to additive manufacturing technologies, and as well for projects involving the development of prototypes and products. Okay, so well, we have some experience in the big context as well of well design, eco design. So here today, I'm going to at least try to provide you some hints on eco design. Some previous concepts that I think that are required to understand how the jump from eco-design to eco-design is given, okay, which are basically product life cycle, how this concept relates to sustainability, what is the role of design in all of this, and its links to eco-design, as I said before, and finally, well, some per 2 or 3 minutes talking about, well, systems, guidelines as ISO 14006 that can help organizations when trying to deal with an implementation and maintenance through time of disciplines as eco-design, okay? So, well, I think that we can start talking about one of those concepts that I was saying that I think that are important to really understand how design can be relevant when we talk about the sustainability about improving the sustainability of our products, okay? So, well, if we talk about product life cycle, well, one thing that I think that it's easy to understand is that, well, when we talk about the product, there is obviously much more than the things that we have on our hands, okay? There is a life before the product reaches our hands, and there is a life even when the product goes by and goes into its end of life stage, okay? Because here we are talking about different stages as the one that you have. Let me just turn the pointer here, okay? You have to think that when we talk about a product, there are different stages that exist on the overall life of that product. Of course, we talk about the production of the raw materials, the transportation of these raw materials to the manufacturers, the manufacturing itself, the distribution of the resulting products to the final users. Well, the life of the product, because the product has a life that can last for days, weeks, years, decades, whatever. And at last, we have a last stage, which is the end of life, which is nowadays very linked with recyclability, circular economy, and this kind of concepts. So if we look at the product through this point of view, through this product life cycle point of view, there are obvious links with sustainability, okay? These links are, I think, more obvious if we just put this same cycle in this way, in a more linear way. Believe me that these are the same stages that we have just seen on the previous slide, okay? If we put like this, because if we put these stages like this, we will understand, or it will be more easier to understand, and each one of these stages is responsible for some inputs and some outputs. I mean, for this product life cycle to exist, there are resources, I mean, energy, consumables that have to be consumed, okay? And there are things that are being generated in this process. The products themselves, of course, but at the same time, we are talking about subproducts, emissions, and wastes, okay? At last, we are talking about, we were talking about a big balance of mass, okay, that is related to this product life cycle. There are elements going in the process. There are elements going out of the process, and at last, these things are energy, raw materials, consumables, emissions to the atmosphere, and other kind of wastes. Okay, all of these things are the ones that are responsible for actually making an impact on the environment. Okay, making a harm on the environment. So now, if we have this product life cycle concept in mind, if we have in mind these inputs, these outputs, these things going in, these things going out that are really, really relevant to when producing an impact on the environment, we have to think now, or we can think now about, well, what's the role on design? What can be the role on design of on these different stages from that point of view, from the point of view of how design can improve or make worse the impact of a product on the environment. Okay, there are some obvious things like in stages, for example, the production of raw materials, the manufacturing or production, as we want to call it, the product lifespan of the product at its end of life. Okay, at least from a point of view, are quite obvious. For example, if we talk about the production of raw materials, if we are dealing with a new design that is, for example, able of lowering the amount of material that is being consumed, it's quite obvious that less material will improve the sustainability of this first stage, as we will be retiring less raw materials from the environment. Okay, it is especially important, of course, when we talk about fossil resources. Okay, resources that in the moment that they are wasted, there is nothing more. We have to recycle them. Okay. This is quite obvious as well, for example, in the stage of manufacturing. Just taking the same example, if we talk about a design that is lighter than a previous one, in the moment that we are using a manufacturing technology, that manufacturing technology is going to spend less time manufacturing that part in the moment that we use a less amount of material. In this stage, you have to take into account that every manufacturing technology is different when it comes to making an impact on the environment. At least, I mean, it's not the same machining as, for example, additive manufacturing. And inside additive manufacturing, as you will know, there are different kinds of technologies, and the different impacts of these technologies lead to different impacts. So in the moment that we change, not only the design, okay, in the moment that we change some aspects of the technology that is required for manufacturing a specific product, we are changing the profile of that stage when it comes to generating impacts to the environment, okay? So, well, changes in design, as you will know, sometimes some changes in design are only possible if we go through technologies as, for example, additive manufacturing. So in the moment that we change, for example, a machining technology by additive manufacturing technology, we are changing the environmental profile of this specific stage. If we go, for example, to the stage number 5, the product lifespan, well, here the modifications on the impact of a product thanks to a change on design will depend basically on if this product is the direct responsible of consuming resources or emitting well, wastes and gases to the atmosphere. Okay, a classic example here on this stage is the case of parts of products that come from the aeronautic sectors, aerospatial sector, sorry. Because in the moment that you have to, a part or a product has to fly, every time this part of product flies, it's consuming a certain amount of fuel. If you are able, for example, to introduce a change on design, so this part or this product is lighter, every time this part flies, it's going to consume less fuel, and as a result of this, it's going to produce less harm to the environment. It's going to be responsible for less CO2 kilograms, okay, every time this part flies. If you multiply this in certain cases for a lifetime that can be as long as 15, 20, 25 years, in these kind of cases, a change in design will be very important for a different behavior in terms of the product, in terms of its sustainability. The end of life, it's another stage that, at least from my point of view, is quite obviously influenced by changes in design. Nowadays that we are talking about the necessity of recycling as much as possible, we are talking about more global concepts, our circular economy. We understand that, for example, if we are able to reduce the number of materials that we use in our products, or we are able to reduce the number of elements that are involved in our product, those are just two cases, that product is going to be more easy to recycle, okay? And that materials that are recycled could go the same product life cycle process, or could enter other product life cycle process, okay? Well, these are the 4 stages where changes in design could be quite relevant for the sustainability of a product. There are other ones, the 2 and the 4, that are related to the logistics, to the transportation of the raw materials of the products, okay? Well, you have to think that in the moment that you change the amount of materials that you require for manufacturing, or in the moment that you change some things related to for example, the weight, the volume, or the geometry of the product, it's quite possible that you are altering the means that are required for taking those raw materials to the manufacturer, or for taking those products to the final user. So at last, the message of this is that design is relevant in all the possible stages of the product life cycle when it comes to the generation of impacts to the environment, okay? So, well, now that we have developed the product life cycle concept, now that we know how important it is for the sustainability of a product, and now that we know that design can play an important role on that, because it can affect all the stages, well, the jump from design to eco-design, at least from my point of view, is not such a jump, but a logic step, I will call, okay? That basically consists on design, okay? Is designing, but taking sustainability into account through the process as another design variable, okay? When you design, you have some requirements. Some are mechanical, thermal, some come from the customers, some come from the industry, etc. But this is taking those into account, but at the same time, taking some environmental aspects into account when you are designing your products, okay? In this case, some of the guidelines, okay, and in this case I'm talking about the international standard 14,006, it even introduces another dimension of eco-design, okay, because this specific guideline says that eco-design is a systematic approach which considers environmental aspects in design and development with the aim to reduce adverse environmental impacts throughout the life cycle of a product. It's quite important that at the same time introduces this systematic approach, okay? Because when implementing eco-design, of course, that we will need some tools, as for example, someone that I'm going to talk just in 2 minutes, as life cycle analysis, okay? You will need some tools in order to be able to compare different options, different design alternatives when it comes to its environmental sustainability, okay? But a very important dimension of implementing eco-design in an organization is thinking that it has to be systematic. I mean, you have there will be in place. You will need not only this kind of tools, but specific ways of working, procedures, a certain infrastructure, internal infrastructure, in order to support an active implementation of eco-design from all points of view. Okay, so well, if we focus now on the specific tools that help organizations when really measuring if a design alternative is more sustainable than another, well, here is where we can talk about available tools, okay? We are not going very further on this, okay? We are just going to provide you some hits of the most important one, or at least the most, that is currently used in our days, which is life cycle analysis, okay? Because tools, you can go for qualitative tools, semi-quantitative tools, or quantitative tools. I mean, when you talk about sustainability, you need to have something that helps you in measuring it, okay? So in this case, maybe the most widespread one is life cycle analysis, which is a quantitative tool, okay? LCA, life cycle analysis, well, maybe if I go back some slides ago, it will be easy to understand what LCA really helps you in, okay? Because, well, if you remember this slide, I was saying that if you see product life cycle, okay, you could see this like as a big balance of mass, okay, where there are inputs, outputs, I mean, things going in and things going out. So the key point of tools as life cycle analysis, as LCA, is that they make possible to transform the data that you have on your product into results that can be measured in terms of different categories of environmental impact. I mean, if, for example, you have this as a process, okay, and you have your streams that go in the process and your streams that go out the process. That streams going in and going out have a specific composition and a specific flow. It has its elements with a certain amount of, with a certain distribution and proportion. Okay, I mean, if you know your process and if you have information on what is specifically going in and going out of your process, this kind of LCA tools, what helps you is on translating that information of your process into results, into figures related to environmental impacts, okay? There is an amount of work that you have to do. I mean, you have to know your process very well. You have to know very well what is going in and what is going out of the process. I mean, you need to know what elements are going in the process, in which proportions, and you have to know what is being generated in your process, okay? So these tools, through 4 phases, definition of goals and scope, preparation of inventory, impact calculation, and final interpretation, helps you to reach something like this, okay? This is just an example, don't take this as well. This is LCA and that's all. Okay, this is just an example. This is just an example that comes from an article that I have referenced in the bottom of this slide. It comes from comparing different alternatives for 3D printing of concrete materials. Okay, just to provide you that context. Here on this graph, what you can see here on bars are the different scenarios. I mean, the different alternatives involving the 3D printing of concrete. Okay, different ways for printing 3D printing concrete. And what you have here on the axis X are different environmental categories. Okay, categories for impact. For example, these are just 4. There are much more. Okay, but here we have global warming potential, acidification potential, eutrophication potential, smog formation potential, and fuel fossil depletion. Okay, as you can see, each one of them is measured in its respective units. But at last, what we can do with this kind of tools is doing this kind of comparisons, okay? Because here we have the 4 different options compared against the different, in this case, 5 categories for environmental impact. So this is the kind of information, that really makes possible to use it when you are trying to decide, to take decisions that involve producing one design alternative or another, okay? This is the kind of information that really makes it possible to take sustainability into account when you're designing, when you're planning a redesign of your products, okay? Because this is the kind of information that really gives you, well, these are not, I mean, this is theoretical data, but they are some good hints of the potential behavior of a product in terms of its environmental impact. Okay, so, well, the final part of the presentation, it's about, if you remember, the definition that was given by the ISO 14006, this part about the systematic approach, okay? Now we are going to focus on that. Because, well, if you are on management standards, as for example, well, the most common one is ISO 19001 about quality, but as you know, there are many others that we call management systems. Okay. Well, in this case, ISO 14006 it's no more nor less than a management system focused on the implementation of eco-design. Okay. So if you are on other management standards, you will know, well, what are the main benefits of this kind of I will call them guidelines. Because one thing about eco-design is that, first of all, if you want to implement eco-design, of course, that you have to change your ways of designing, okay? You have to introduce some things that you usually don't use when you are designing a product or redesigning an existing product, okay? You have to change your ways of working. So whenever you have to introduce some changes, you will have to change something in your day by day. Maybe you need to create some roles into the organization, and you will have to provide you with some indicators about if you are doing great or not in terms of producing, well, of being more sustainable in this case. Okay, it's not only about buying an LCA software, making LCAs, and that's it. No, it's really about, well, first of all, the organization knowing what is its specific purpose when it comes to being more sustainable. I mean, what does the organization wants to achieve in terms of sustainability of their products, okay? Because there are different options, all of them valid, okay? But at last, well, these kind of guidelines provide you with some backup when trying to implement these kind of things. And more important than that, not only implement, but maintain them through time, okay? Because, well, from the point of view of the structure of this guideline, of this standard, as I said before, if you are on this kind of management systems, well, this would not surprise you, okay? Because it's quite a traditional quite a traditional structure that in a first part it starts with talking about the general terms and the reference for understanding the context of this standard. A second part which is about the general context that the organization has to create in order in this case to implement eco-design. Here we could talk about context, the leadership and the planification of the overall activity of eco-design. In this case we have a third section about the actual resources that have to be implemented in order to make the implementation of the eco-design possible. A fourth part about, how to keep on track with eco-design, how to measure the results of that activity, on how to improve that activity through time. In this case, in the specific case on this standard, a last part about providing some specific hints on implementation of eco-design on design processes. Okay, but the important thing about eco-design, and not only about this standard, okay, I'm here talking in general, is that of course all of this is for environment. I mean, that is something that, in the moment that we introduce in one product a change that, for example, promotes a reduction of the consume of resources or avoids the emission of pollutant gases, for example, of course that we are working for the environment. But at the same time, an organization as an entity that wants to make an economical benefit has to look for the reasons that from that organizational point of view has to be marked in order to make eco-design implementation sustainable through time. Because at last are the results of eco-design, the results to the organization, the things that make sense when implementing eco-design, okay? Because here there are some questions that can be proposed just for every organization to look for the actual reasons for eco-designing, okay? For example, we could talk about, maybe we want to increase the rate of reprocessed end-of-life products in order for expending less in new raw materials. Maybe we are talking about simplifying our designs in order to reduce manufacturing cost. Again, decreasing the consumption of pure raw materials. Maybe it's something about the image of our product in the market, okay? Is a reason as good as any other, okay? It can be in place as well. And we could look in other terms for another cross advantages with collaborators, with providers, with customers. I mean, reasons we could here enumerate dozens and dozens, okay? But one thing when you implement eco-design is that you are aware that it is not only about buying a software and then doing indiscriminated life cycle assessments. Now, first of all, is to be very clear for everyone and for oneself in the first place. What is the sense for the organization when we talk about implementing eco-design and making our products sustainable? Okay, because all of this will have to translate sooner or later into something like like these kind of questions. Okay. So, I don't know if more or less I have adapted to the 20 minutes. I hope so. If not, I beg your pardon. So, I don't know if we have time now for questions, and if not, I will be very glad to answer them at the end of the whole session. So, yes. Thank you very much.
Thank you, David, for your presentation, and thank you for clearly showing that sustainability starts from the very beginning, from the design, from the conception of the part and the product. So thank you for this very interesting presentation. I would suggest to move to the third presentation, and maybe we can leave some time for questions in the end. So let me introduce the last speaker, who is Dr. Ioannis Kokinopoulos from HIRES, Innovation Research and Engineering Solutions. He is a specialist in the field of safety and risk assessment with a special focus on additive manufacturing technologies. And the title of his talk is Fuse Filament Fabrication, 3D Printing Emissions and Safety Strategies. Ioannis, I leave you the floor.
Thank you very much. Can you see my presentation?
Not in slideshow mode. So if you prefer, I can show it with my screen, and you can just tell me
okay.
To move to the next one when you're ready. So let's do that. Okay.
Okay. Thank you very much again for the invitation and for organizing this webinar. Here you can see our presentation about fused filament fabrication, 3D printing, emissions, and safe strategies. Okay, here you can see also a brief outline of the presentation that I'm going to present you. And if we proceed in the next slide, we will talk about sustainability elements of FFF 3D printing. Continuing, we can see from this particular slide for a technology to be considered sustainable, it should possess benefits in these specific sustainability elements, as you can see in the chart, in the pie chart. Specifically, regarding FFF 3D printing and focusing on sustainability elements, if we move to the next slide, on sustainability elements such as recyclability and circularity, environmental impact, social impact, and cost effectiveness, we can see in detail some ways that 3D printing can help us become sustainable and go green. Moving on to the next slide, here you can see that firstly, 3D printing can make parts locally. 3D printers can fit even in an office, so we can make parts, prototypes, and products locally as opposed to shipping them from far away. The result is less environmental impact from planes, ships, and trucks, so we will reduce emissions. Moreover, it contributes, as you can see, to smaller and quieter factories. One 3D printer can replace several pieces of traditional manufacturing equipment because it can print a wide variety of parts in a wide variety of materials. So less equipment makes for smaller and quieter factories and also, again, fewer emissions. Now concerning repairability and spare parts, 3D printers can quickly and cheaply make repair parts for unique and even out of production equipment, keeping all machines of the scrap heap and eliminating simultaneously the need for more raw materials and energy to manufacture new machines. It also contributes to more efficient design. 3D printers can make parts with shapes and features unachievable with other manufacturing techniques. We can redesign our part to make it more efficient and use less material. Products that were once made of multiple parts can now be printed as one, thus reducing material and time. And now about streamlined manufacturing. 3D printers require fewer tools and processes than traditional manufacturing, thus eliminating in this way a lot of equipment and mainly, again, energy. It consumes also less raw material. It can make parts with only the material needed and minimal support material instead of carrying a part from a block of metal or plastic, which produces more waste. And finally, it eliminates inventory. We can print on demand or print small batches instead of having a warehouse of spare and overstock parts, many of which may never be needed. Okay, if we go on, if we go to the next slide, we can see.
Let me just say that unfortunately, it seems I can have no control at all on this file apart from moving from one slide to the other. I don't know if there is any constraint on that. I hope that it is clear even if we go on in this way. Sorry for this inconvenience.
Okay. Yes, here we're going to talk about another sustainability element, the occupational safety on FFF 3D printing. Yes, in this chart you can see the additional element. Sorry. The presentation I can see.
Can you see it now in presentation mode?
Yes,
Yeah.
yes.
Okay, perfect.
Thank you, Gabriele. So we can move, I think, to slide 9.
Okay. Yes, we were talking about occupational safety on 3D printing. Yes, perfect. You can go to the next slide. Okay, and we're going to analyze this particular sustainability element of 3D printing. Okay, in the next slide, we can see that, as we all know, fused filament fabrication is the most widely used additive manufacturing technique so far. It is used in homes, in schools, libraries, universities, but also in occupational settings. But what about occupational safety? It is considered as a safe process, but what does the latest research show us? In fused filament fabrication, a solid thermoplastic filament is deposited through a moving nozzle heated close to the filament's melting point, as you can see in the next slide. The hazards attributed to fused filament fabrication mainly regard hazardous emissions caused by thermal degradation and decomposition of the polymer filaments. These emissions includes ultrafine particles, particles that are smaller than 100 nanometers, which are emitted in significant numbers during the printing procedure. Their increased specific surface area and lung penetration potential can lead to a multitude of health issues as a result of exposure. In addition to this, emissions also includes volatile organic compounds, VOCs. These are highly reactive gases, which can result in short or long-term adverse health effects. For example, VOC emissions of ABS filaments consist mainly of styrene, so it's very harmful to our lungs. And moreover, included filaments additives may also be emitted during the printing procedure. If we go on, we can concentrate on ultrafine particles, and we can see that concerning UFPs, respiratory tract is the main exposure pathway, and deposition of particles to the lungs highly depends on the ultrafine particles' aerodynamic diameter. And according to Oberdoster et al., and multiple path particle dosimetry clearance models that you can see in the picture of inhaled particles, we can see that larger size particles that are over 1 micrometer, tend to deposit mostly in the inhalable, we say the nasal zone, whereas the smaller size particles that are below 100 nanometer, deposit in the tracheobronchial and alveolar regions of the lungs, deeper in the lungs. These smaller sized particles are blocking the alveoli mainly, and may lead to many pulmonary and cytotoxic effects to the lungs, such as inflammation, fibrosis, and at last even lung cancer. Particles below 20 nanometers also can pass through the skin, introducing in this way also a skin and ocular hazards. Now concerning VOCs, several VOC species, volatile organic compound species, can be emitted depending on the composition of the filament that is used. For some filaments, the emitted VOC species do not present a risk, as is the case for lactite, as you can see from the chart, which is emitted from most PLA filaments. However, many of them, like styrene and caprolactam, which are emitted from ABS filaments, can result to acute or chronic adverse health effects. In the following slides, we are going to describe the equipment and methodology we use in order to measure ultrafine particles and volatile organic compounds. Okay, now regarding the methodology we are employing, it is based on the ISO for nanotechnologies and health and safety occupational practices. In this approach, on-site measurements make up the core of the assessment. Measurements can be described in three parts: before the start of the process, we record background concentrations for about 30 to 60 minutes, and later use them as a control against which the other values are evaluated. Next, following this, concentrations are measured during the process and after its completion until the values return back to the background levels. Measurement campaigns are categorized into types: emission and exposure. For emission measurements, the instruments are placed near an enclosed emission source, and the goal is to compare different materials and parameters. On the other hand, for exposure measurements, are performed with instruments near the operator's breathing zone or are located in a near-field, far-field configuration. From exposure measurements, we can evaluate the risk by comparing the exposure levels with the respective limits. And in this slide, you can see the equipment that we, in the previous slide, I'm sorry, you can see the equipment that we use in the picture. Exposure campaigns were performed using these instruments that enable the measurement of number concentration for particles between 10 nanometers to 25 micrometers, size distribution from 10 nanometers to 420 nanometers, and total VOCs concentrations. And in the next slides, we will explore some results of various exposure campaigns with a focus particularly on ultrafine particles. During this, the first campaign, you can see that a commercial 3D printer was used and 3 candidate prototype filament materials were evaluated in terms of their comparative ultrafine particles emission potential. The impact of nozzle temperature regarding the magnitude of emissions were the main parameter that was evaluated. As we can see from the diagram, each color corresponds to a different material, and there can also be seen the different nozzle temperature settings used for the printing for each of these materials. The main emission peaks were observed during the print start. Two very important conclusions extracted from this campaign were that emissions are greatly impacted by the material type, firstly, and most importantly, that higher nozzle temperature always leads to higher emissions of ultrafine particles. If we continue, we can see the second campaign. This campaign consists of 2 measurements during the operation of a customized printer for the co-deposition of PLA, polylactide acid, and carbon fibers. First, we will analyze the case without any engineering controls at all. As you can see from the diagram, the 15-minute moving average, represented by the green line in the graph, exceeds the recommended short-term exposure limit during the whole process, reaching values as high as 3 times the limit. Emissions of significant concentrations of ultrafine particles were confirmed. And as we can see from the diagram again, emissions during carbon fibers and PLA printing are higher, peaks at around 450,000 particles per cubic centimeter, as you can see from the red, from the yellow part of the diagram, the painted yellow, compared to emissions where only PLA is used, peaks at around 300,000 particles per cubic centimeter. Moreover, as you can see on the 2 charts at the bottom, size distribution analysis results indicate that there is a significant difference in the ultrafine particle size distribution before printing and during the print activity. Comparing the ultrafine particle size distribution during printing with that of background, it can be confirmed that nanoparticles of very small sizes are emitted during printing, approximately 10 to 15 nanometers in diameter. And the concentration also of the emitted ultrafine particles is also very high. In this slide, we can go over a measurement during the same process, but this time with the application of engineering controls in order to mitigate exposure. In this case, the printer was moved to a room of similar volume, but with a general dilution ventilation of 10 air changes per hour, and a local exhaust ventilation. An arm hood, as you can see from the picture, was also available. We can notice that the 15-minute average ultrafine particle concentration was kept under the recommended limit during the whole process. Moreover, concentrations, as you can see, are much lower, with peak values being about 4 times lower than without engineering controls. So through using this setup, a significant mitigation of exposure was achieved. So to sum up, given the previous slides' very high emission values, and for the purpose of emission removal and exposure mitigation, as we have said before, the experiment was repeated after applying general dilution ventilation with 10 air changes alone, and then general dilution ventilation in combination with local exhaust ventilation, the arm hood, as you have seen from the blue and green highlighted parts of the diagram. Concentrations during carbon fibers and PLA printing were significantly lower. As you can see, the peaks are at around 100,000 particles per cubic centimeter with general ventilation alone. The blue part of the diagram, and 80,000 particles per cubic centimeter with general ventilation and the arm hood in presence, the green part, compared to previous slides printing emissions with no engineering controls at all, where peaks were around 450,000 particles per cubic centimeter. So we have achieved mitigation of exposure. If we proceed, here we will have some general consideration conclusions. How can we protect ourselves against ultra-fine particles exposure at the end? Here we will describe the hierarchy of control scheme that you can see in the slide. In every workplace and every piece of equipment has some level of risk or safety issue associated with it. The hierarchy of controls is a system used in both environmental health and safety to minimize or eliminate exposure to the hazards. Based on this hierarchy of controls scheme, we can understand the priority of engineering controls in terms of providing a safe work environment in comparison with administrative controls or personal protective equipment. Personal protective equipment, as you can see, is considered the last control barrier that we can use. If we focus on fused filament fabrication 3D printing technique, and particularly on how to implement various engineering controls in order to mitigate the exposure to hazardous emissions of ultra-fine particles, we can conclude on some general considerations presented in this table. General dilution ventilation of about 4 to 6 air changes per hour is highly recommended for the mitigation of the exposure. Moreover, simple and inexpensive HEPA filter air purifiers can assist in removing the aforementioned emissions. Local exhaust ventilation systems, as arm hoods, can also be applied, as we have seen in the previous slides. Now, for non-enclosed printers, a custom enclosure can be designed appropriately in order to mitigate further exposure. And finally, it is recommended to use the lowest practically possible nozzle temperature in order to reduce emissions. And also, a higher level of caution is recommended when working with additivated filaments. Last but not least, personal protective equipment such as FFP3 respirators, goggles, lab coats, and gloves must be used in order to provide protection against inhalable, dermal, and ocular exposure. And if we go on, some conclusions. Here you can see. We can say that as a conclusion, fused filament fabrication 3D printing is an established manufacturing technique in the modern workplace. However, it entails emission hazards of ultra-fine particles and volatile organic compounds. The emission exposure profiles vary for different cases and parameters, as we have seen in the aforementioned campaigns, and also exposure measurements are necessary to define them. Nozzle temperature and material type are the most important determinants for the emissions, as we have seen. And also, engineering controls can greatly decrease the exposure to the hazardous emissions and their proper configurations should be examined very thoroughly. To sum up, by studying and addressing the emission hazards, we can ensure the sustainability and also further evolution of this highly promising technology as fused film fabrication 3D printing. That's all from my side. Thank you very much for your attention.
Thank you, John. Thank you, John, for this interesting presentation on the importance of measuring emissions in processes and having quantitative assessments of all these kind of aspects. So we have only few minutes left, so please find in the chat a link where you can find a survey. We would like to kindly ask to go through this survey to provide us with your feedbacks about this webinar. They are very important, so please take it. It takes just 1 or 2 minutes, but it is very important for us. And there is, I would spend the last few minutes, there is one question in the chat from Rachel. She's asking, this is one for John. Do these measurements, equipment, and methodology apply to other technologies, not just in FFF?
Yes, of course. All the measurement equipment and the methodologies also can be applied to other technologies and not only for the fused filament fabrication. We can measure all nanoparticles that are emitted from all techniques that are used.
Okay, thank you. And maybe one very last quick thought from David. So you talk about design, and we are in the framework of SEM. So we need to fill a gap of skills on design for additive manufacturing. Do you have some thought on that?
No, well, completely, because well, in the first presentation, Bianca was talking about additive manufacturing and some uncertainties that are related from the points of view of the industry about, for example, not perceiving additive manufacturing as a reliable technology. At least from my point of view, that we have industrial additive manufacturing machines for now 13 or 14 years, the machines work very well. The machines are quite reliable. What you need is someone that knows very well how to design for that technology. The problem is not the technology. The problem is the lack of skills, the lack of capacities of experience of people adapted to that technology in order to make the part fair well at the first time, and avoiding all the problems that she was talking about. And yeah, it's about all about the skills. It's all about the skills and shortage of skills. Yes.
Yeah, we know this very well. Okay, so thank you. I think we are pretty over with the time. You can find also the link in the chat about the upcoming webinars. If you can visit our SEM website, you will find out the recording of past webinars and the link to the next one. So you are very welcome to visit our website and to attend our events. And I would thank Gabriele for his very helpful support. And I would thank our speakers, David and John, for their very interesting presentation. Also, thanks to Bianca, who had to leave us. And thank you all for attending. I hope you have a nice day. Bye-bye. Thank you.
Thank you, Marco. Thank you, everyone. If you have any questions, please reach us out. And thank you again, all the guests, for the very insightful speeches of today. So see you in the next SEM webinar. Have a nice day.
Have a nice day.
Bye-bye. Bye-bye.
See you.
Bye.
Bye.